The swap?
Okay, so basically, if you look at the Heisenberg exchange interaction and you have two spins at adjacent sites, then if you turn on the exchange interaction for a certain time, for instance, if it's a constant, yeah. You have a question?
No, I'm just trying to follow what you're saying. I don't see this at all. Is J of t in their control?
J of t is, yeah, controlled.
But it's not spatially dependent.
It doesn't have to be. Well, okay, so if you're talking about quantum dots, say single electrons in adjacent quantum dots, then basically you can change the value of J, for instance, by changing the potential barrier between the dots. And so basically that will change the tunneling between the two dots. And so the virtual tunneling.
So you do have spatial control over the value of J.
So you have spatial control, but the point is that in the case of single spin qubits, which are widely studied right now, localized single electron spin qubits and quantum dots, is that you have to have spatial control on the length scale of a single quantum dot, and so that becomes a big challenge. So does that?
So in your model, you're assuming that you have just some pre-existing J's between various spins, and you're trying to work out a way to make a gate or make a flying qubit or something without having to access individually each one, right?
Right.
Yeah.
Right. Okay. So, so to study the ground state of this system, we can look at the spin density. And if we initially let one of the exchange constants be 0, then we have a single spin at the center that's surrounded by isolated spin dimers on either side. And the non-zero spin density in this case is localized entirely at the center spin. And if we now increase the value of one of the exchange constants relative to the other one, which means that we're coupling the spin dimers more strongly to the center spin, then the spin density becomes more and more delocalized. And so this gives us a method for converting between localized and delocalized qubits by varying the exchange dimerization strength. So we can also generalize this pattern of exchange couplings by using an exchange profile like this in order to design a quantum field. And from the staggered order parameter for this case, you can see that there's a domain wall. And the spin density of the spin-up ground state is localized around the center of that domain wall. And this represents a single spin 1/2 qubit. And the state is in fact analogous to topological solitons that exist naturally in conducting polymers such as polyacetylene. So now that we've seen how we can create a topological soliton-like qubit, we can look at what happens to the system when we introduce local disorder into the exchange constants. And so from the staggered order parameter for this case, you can see that the domain wall appears distorted, but the spin density remains localized around the center of that domain wall. And we find that this is true in the case of up to even 50% disorder in the exchange. So if we now want to look at the effect of moving the domain wall, we can consider a closed ring of spins. And if we calculate the spin density of the spin-up ground state as a function of the domain wall position within the ring, then we find that as the domain wall is moved around the ring, the localized spin density travels along with it. And we also find that there's a finite energy gap separating the ground state from the first excited state for all of these domain wall locations. And we can also move the domain wall within the disordered system, and we find that even in this case, the spin density remains localized around the center of the domain wall. And so this gives us then a mechanism for producing flying spin qubits entirely within a solid state system that's also highly insensitive to local perturbations of the exchange constants.
So how do you move the domain wall?
Okay, so I was actually just going to get to that. So we can also construct this quantum field within a physical system using a one-dimensional array of elliptically shaped quantum dots containing single electrons. And if we apply an electric field transverse to a pair of these dots, then depending on its direction, the electron wave functions will shift so that they overlap more strongly or more weakly. And within a one-dimensional array of these dots, we can produce dimerized exchange. So in addition, it's also currently possible to create precisely controlled arrays of quantum dots, such as these dice patterns of germanium dots on silicon, which are currently being studied by a member of our group, Dongyu Yang. And so if we can now produce an electric field profile by gradually varying the form of the electric field between these two extreme cases, then we can produce a field profile that maps directly onto this staggered order parameter, and a localized qubit will be produced at the point where the electric field reverses its direction. And by propagating this electric field through the system, we can produce flying spin qubits. So is that clear?
Almost. So you can control electric fields at nanometer scales, can you?
Yeah, well, I mean, people have been working on that for single electron spin qubits in quantum dots. So they have
But
shown
that's
that
a
they
larger
can
length
control. But
scale.
this, yeah, so this is actually on the scale of this whole system, not on the scale of a single dot. So you're actually applying a kind of a global electric field, which gives rise, because of the geometry of these quantum dots, it gives rise to the exchange pattern that we want.
Right. Has this been implemented?
Not yet, but
Okay. I'm seriously worried it could succeed. You need the zero to be at the right place. And if it's smeared over several of those things, then the whole topological nature of this thing vanishes.
well, no. So it's actually it's the state is actually that's the topological nature of it, is that the state is actually associated with the whole system. So the spin half ground state is associated with the whole system. The only thing about the localized spin density is that's the region where you can access the quantum information from. But that you can have some flexibility on how wide that is. So does that?
No, it doesn't.
Okay. Okay.
So let me be more precise. You create the spin that stands out, the one that causes the domain wall to exist, by this location of the zero in the electric field, and nothing else. Is that right?
So it's the overall form of the exchange that we're introducing into this. So it's actually, I back up a little bit. So it's actually the fact that there is this domain wall in the whole system. It doesn't matter so much how wide it is, how many spins it covers,
Right.
but it just matters that there is a domain wall in the
Okay.
system. And so that localizes the spin
So if
density
you
on
had
some scale.
two spins in the middle
Uh-huh.
who are out of sync,
Sorry, what do you mean by
so
out
you've
of
got
sync?
one spin right there,
Uh-huh.
put two of them right there,
Okay.
then what happens?
So are you saying that,
The even case?
Yeah.
Is
Even case.
Two domain walls.
so yeah, so then you would have two domain walls. You'd have a pair of domain walls. I was actually going to get to an example of that. But you would have two kinks or two domain walls, and so you'd have two qubits associated with the system instead of one.
So what's topological about this?
So it's basically the fact that you have this qubit encoded in the system, no matter where the domain wall is, no matter how many spins there are in the system.
But topological means something more, right? It means
Well, it's topological in the sense of these topological solitons, for example, which
I don't know what the topological is.
So okay, so I mean, they're states which are basically excitations of the system as from basically the fact that you have two dimerized configurations possible in this system. And so if you have two degenerate dimerized configurations possible, then you have excitations out of that subspace that are these topological excitations. But it's not topological order in the sense that people talk about in a topological quantum computation.
So if I were to think about this, you have some, if you go back to one of the earlier slides where you showed like, you know, the gapped system versus the ungapped system, right? Like, you know, you had those multiple, yeah,
This one?
like this one, yeah. So you're in the other one, right? That one.
So for the
You're-
qubit, we're in this one.
Oh, you're in that one?
Yeah,
I'm
the
sorry.
odd number
Okay, I
chain.
missed that, I see.
So
Uh-huh.
for 2 qubits, we would be.
And so what you're saying is that those two states there
Mhm.
are topologically protected for excitations out of that subspace?
Well, these particular states are actually associated with a spin cluster qubit, so
Yeah.
they're actually associated with only a finite number of spins. So this is not exactly the same thing as
Okay.
our system.
Uh-huh.
But because we have this dimerization, oops,
Yes.
I'm going backwards instead of forwards. Yeah, so, I mean, because we have this dimerization and degeneracy in that dimerization, we have this topological state.
I guess I'm looking for a similar graph of like energy versus,
Okay.
something like, just
Yes.
like how you had for that one. To understand
Okay.
what your qubits are, so.
Okay, so
you're-
so I mean, you can think of them as similar to those states,
Yeah.
because here we're always calculating it for a finite number of spins.
Yeah,
But, and those two degenerate ground states exist even if we have this dimerization.
okay.
But, they're basically those two degenerate ground states that have total spin 1/2.
Okay.
And so they do have a finite energy gap to the first excited state, just like a spin cluster qubit.
And that gap is protected, is that what you mean?
It protects the qubit,
Okay.
yeah, from processes that
And that
don't
is the
conserve it.
topological protection, or not?
It's not
Not in the way
topological
that
protection.
people talk
But
about.
it's protected energetically.
Energetically it's protected,
Energetically,
Yeah,
it's
but it's
protected.
not topologically protected.
No.
No.
The
No,
disorder
I don't
and
think
so
she
on
said that.
mess that up. Okay, I see.
Yeah, well, yeah,
So
so
what does
particular
disorder-
types of disorder mess it up. So
Uh-huh.
if you have disorder in the exchange, we find that for this method, it doesn't really change anything.
So
But-
what kind of disorder messes it up?
So if you have anything that breaks the total spin and total z component of spin symmetry, so if you have, for instance, inhomogeneous magnetic fields in the
Yeah.
system, that will change the quantum number. And
Okay, but you don't have to worry about, say, one dot being slightly different than the other,
No.
because that exchange term is
Exactly.
protected. Okay,
Exactly.
all right, thank you.
So if an H atom comes and bonds to your quantum dot, does that kill it also? Because now you go from odd to even, right? If you actually have a
Yeah.
radical
Right,
chemical
so-
species attached?
Yeah, you would go from, so within a finite system, yeah. So, but if we envision a very, very, very large system, it shouldn't matter eventually whether you have an even or an
Even
odd
or odd.
number of spins. Okay, so the properties of flying spin qubits that we've looked at so far were obtained numerically, but we can also describe flying spin qubits analytically using an exactly solvable model for a domain wall in an antiferromagnetic 3-spin ring or spin triangle with an exchange profile of this form where J0 represents uniform exchange that's modulated with an amplitude J1 and a phase phi corresponding to the domain wall position. So without this modulation of the exchange, the spin triangle has a 4-fold degenerate spin 1/2 ground state with 2 possible z components, which we call spin up and spin down, and which are each associated with 2 states that define a pseudospin. So modulating this exchange causes a splitting into ground and excited states within each pseudospin space. And the spin triangle now has a ground state doublet that serves as a single qubit, and which is also protected by the finite energy gap that's independent of the domain wall position phi. So we can look at what happens to the qubit within a particular pseudo-spin space as we move the domain wall, and here we again choose the spin-up subspace. And so for phi equal to 0, the domain wall is at site 3, so that spins 1 and 2 are in a singlet state, and the spin density is localized entirely at the domain wall position. And this non-zero spin density moves along with the domain wall as it's transported around the ring. So by shifting the domain wall position, we're changing the orbital-like character of the ground state. And so we see that this pseudo-spin space actually represents an orbital degree of freedom for the flying spin qubit. But regardless of where the domain wall is within the system, the qubit remains encoded in the total spin of the ground state for the entire ring. And it's in fact this lack of coupling between the spin and orbital-like degrees of freedom that allows us to not only produce flying spin qubits, but also to tailor 2-qubit interactions. So we can also look at the time evolution of the qubit by moving the domain wall at a constant angular speed omega. And the motion of the domain wall in this ring, because it's periodic, is described by a time periodic Hamiltonian. And so we can use Floquet theory to describe the dynamics, which is analogous to using block theory for spatially periodic Hamiltonians. And so we can initially start with the domain wall at this point and allow it to make any number of full revolutions. And then we find this exact result for the Floquet state associated with the ground state. And here you can see it's a combination of both the initial static ground state and either the plus or minus state, depending on which way the domain wall is moving. And the contribution of this plus or minus state depends on the ratio omega over the gap delta. So that if the domain wall is moved rapidly, then the state of the system within this pseudo-spin space moves out of the xy plane and toward the z-axis. On the other hand, if omega is much smaller than delta, then the state remains very close to the initial static ground state. And so this gives us an adiabatic limit for the motion of the domain wall. And so we see that we've been able to gain some insight into both the static and dynamic properties of flying spin qubits using this exactly solvable 3-spin model. So we can also generalize the method of producing flying spin qubits by designing a quantum field which has 2 domain walls. And so if we initially start with a fully dimerized system, and then by creating a soliton, anti-soliton-like pair of domain walls and moving them apart, we can spatially separate the 2 qubits associated with them. And if we compare this plot of the exchange profile with this one, which shows the spin density for a linear combination of the ground and first excited states, then we see that the qubits once again follow the motion of the domain walls. And if we look at this energy spectrum, then we see that there's an exchange splitting in the energies of the lowest 2 states that falls off rapidly as the domain walls are moved apart. And because the Heisenberg exchange interaction conserves both the total spin and the total z component of spin for the system, we know that the 2 qubits will remain in a singlet state as they're moved apart. And because the singlet state is an EPR pair, which is an entangled state, we now have a way of efficiently generating a physical resource. So now we can consider how it might